Greetings. In this one, I will focus on the rank nullity theorem, and I will provide two examples to show it in practice, that it works out and that it's true. And that it actually can be used to shorten some calculations and so on. First of all, to make it clear, rank nullity theorem, I will present that example, the example number 1 by the way already. Namely, this one will be quite simple and quick. So, rank nullity theorem says that I will call rank R, if this is matrix A, then R of A is the rank of A, and capital N of A is the nullity of A. Let me define the notation this way. It will all equal to N, where N is the number of columns of A. So what it says, rank nullity theorem basically says that the rank of a matrix plus the nullity of the same matrix equals to the number of columns it has. Now, we should also define the rank and the nullity. So rank is the amount of linearly independent columns it has, and the nullity is the dimension, so basically the dimension of the column space. And we can get there by row reduction and identifying how many columns have pivot, how many columns are so-called pivot columns, or also in this case it's even quicker to identify that actually one column is straight out a linear multiple of the other, and so there's just two, and both mean the same thing. And for that reason, all of it that this column space of this 2x2 matrix has is spanned by 1. So the rank in this case will be 1, by the way. For the nullity is the dimension of the kernel of the matrix. So it's the dimension of the equation AX equals 0, where X are the vectors that will fulfill this equation, 0 being 0 vector and A being the matrix. So what is the dimension of the vector space? So how many vectors are in the base of what will generate all of its linear combinations, all the possible vectors that will be compatible for this equation. And so null space kernel, that's a thing that I would recommend to know all this before going to the rank nullity theorem. Basically, here the requirement is to know what is the rank and what is the nullity, and then here it's just putting it together. So first of all, as I said, I will look concretely here at examples. So actually I will talk about the rank of A, and then in that relation to the nullity, and reflect it with this statement. So the rank of A is 1, and the reason is that both of these columns mean the same thing. One is the multiple of the other, therefore the columns, there's just one of them required. The amount of linear independent columns is 1. The other one is dependent on the other, so I could say that this one is the independent one and this one is dependent on it, or the other way around. Both are legitimate in the same way, but one of them will always be redundant. And then N of A is the null space of the matrix, which is the dimension of the kernel. And how do we get there? Well, actually what I can do is something I could also do in the first step, where if I'm looking for the rank, is I can do a row reduction of the matrix. So I will row reduce it, I will subtract one row from the other. Actually here it ends up being the way that one row is the multiple of the other row again. So 1, 2, 0, 0 will be the result of one step of row reduction. And from that I see that, okay, here could be a pivot column, but this one not. And so we have one pivot column that already told us the rank is 1. And the nullity, well, now we can directly solve for it, because only thing we have left, we're looking for some xy that satisfies that equation AX equals 0 here. What is that xy gonna be? Well, this row is all the information we have, because the second one is just zeros. What it means is this is the x column, this is the y column. So x plus 2y equals 0. And now I will basically take my column vector and I will use one of the variables as a parameter, because as long as I have one equation but two unknowns, I can only solve for one of them, and the other one has to be a parameter. I cannot have an explicit solution, number-based solution for both of the variables. So I will keep x as the parameter, and y will be the y will be dependent on it. So y will end up actually being minus 1/2 x. So my vector solution for the kernel is x and minus 1/2 x. And in this situation, what one does is takes out the common variable to make this vector only contain constants. So what it says, this is the whole vector space of the solution for the kernel. There's just one dimension because there's one constant evaluated vector that is multiplied by some scalar. So it says it is the span of this one vector. Because it's the span of one vector, the dimension of this whole kernel is 1, because it is spanned by one vector. So nullity is 1, because nullity is the dimension of the kernel. And yes, it goes back to the expected result, because here in this case it's 1 plus 1 equals 2. The amount of columns we have for the matrix are 2. There's rank of 1 and nullity of 1. So it goes together and it works the way it was expected. And now I'm going to illustrate the exact same thing with another matrix that's a little bigger. So 1, 4, 1, 2, 1, 1, and 3, 0, 2. 3, 0, 2. And now what I can do is do some row reduction first. So again, rank plus nullity of the matrix must equal to the amount of columns. Some row reduction that I won't comment much on, because that's again something that I would recommend knowing before going to such a topic, otherwise one will get really confused. Alright, and now I can proceed to the last step, kind of. Well, already here I would, we can do 2 more steps. So I will divide the second row by 7, minus 7. Third row is left. Then I add the second row 12 times to the third one, and we'll get 3 pivot columns. So these are row operations, and I would highly suggest or recommend practicing this. This is useful because it leads to all these various results in linear algebra practice. So 0 minus 12, well, I add this 12 times row 2 to row 3. 12 sevenths minus 7 sevenths is 5 sevenths. Or in other words, I'm adding the 1/7 12 times to minus 7 over 7. Alright, so now we have this, and yes, we see all 3 of these columns are linearly independent. And this is interesting. So now in this case we will have this eliminative scenario. So the null space of A, first we should, okay, I'll put a question mark here. First, the rank that we now identified. The rank of A is the amount of linearly independent columns, and all 3 are linearly independent, so it's 3. But what we know is that n equals to the rank plus, in this case I'm running it the opposite order, but it doesn't matter, it's commutative addition, of course. So n of A is still unknown, quote unquote, and rank we found out 3. But n is also 3 because n is the amount of columns. So actually this will let us have a very clear conclusion here. N of A must be 0. So you see, you can get one of these pieces of information, and by knowing this theorem you can get to the other piece without much work. But let's also prove it, or at least prove it for this case, or see why it is so. Why it ends up so, or at least show that it ends up so, really. So what we're expecting, that the null space has a dimension of 0, because that's what nullity is. Because rank already took all of the size of the n, the lowercase n being the amount of columns of the matrix. Well, it is so for the simple reason that we want to make this equal to, we multiply by some vector xyz, want to make it equal to 0, 0, 0. And here, if I augment it, I will get this matrix and then another last right column 0, 0, 0. So z times 5 over 7 will be 0. So z will be 0. And then I proceed to the second row. Then it will be y plus 1 over 7 times z equals 0. But z is 0, so it will be y also 0. So that's y. And then x will go the same way, so x will also end up being 0. So we will have 0, 0, 0, the trivial solution. So basically there's not any special vector that would span something. It's just 0, 0, 0, the trivial solution to this question. All three columns are linearly independent. The only way to get this solution to this homogeneous equation equaling 0, 0, 0 is to have all columns basically cleared out by multiplying each of them by 0 of a scalar. And that's the idea here. So if our rank is the same as the column number of columns, it means all columns are linearly independent. We have a fully linearly independent space for these three columns, and so there's 0 dimension for the null space.